backpropagation relies on the fact that in a neural network we have nested function. So if you recall, the chain rule from the derivatives is basically an application of the chain rule to neural networks. So it allows us to compute the gradients with respect to the each input of each node. So it makes derivatives local, which makes them easy to compute because each node we only care about their input and our output. And this is basically what we refer to as the backward phase. So as you can see here in the diagram, the input, the derivative of this node with respect to the loss function can be decomposed into to find the derivative at this location. This can be decomposed between the input and the local derivative at this node with respect to its inputs. So it makes it really easy for us to compute derivatives in a neural network. So considering how all these computations happen in nodes, it makes sense to view neural networks as computational graphs. So basically, this is the way that a lot of machine learning frameworks view neural networks. And they have a lot of similarities because both they have compute nodes, they have edges that connect those nodes, they have a direction in the flow of information, and they are organized in layers, and that makes it easy to cast them as computational graphs. So in a computational graph, then, in this example, the computation of the forward ways of this network would be that given the inputs, we compute all the neurons at that particular layer. And then, given that we have no cycles within that layer, of course, then we forward all the results into the next level, where we also compute the output of each node, and we do that for all the layers in the network. Notice, however, that when we have dependencies and some layers have to be computed before others, then in that case, our computational graph, we structured it in such a way as to have a clear view of what operations can be done concurrently and what has to be done in order. And when we write it in such a way, it makes it easier to program in a machine like a GPU. The same computational graph that we have for the forward phase can also be applied to the backward phase. So the forward pass is computing the dot products between the weights and the inputs, and the backward pass basically propagates the loss value through each node and through each layer, and implements basically backpropagation. So it multiplies the incoming gradient with the derivative at that node. So here is an example of backpropagation in one dimension. So this is a very simple node just to illustrate the process. So first, a reminder that the weight is updated based on the learning rate, and the value of the derivative of the loss with respect to the weight. So first, we decompose this this derivative into the derivative of the loss function times the derivative, the local derivative at that node. Then, if we use the sum of squared errors as our loss function, it can be decomposed like this. The output of the node can be computed by a simple dot product, and the derivative of the node is, with respect to the weight, is turns out to be the input. So first we perform the forward pass to find the loss value, assuming that we have these values and our target value, the ground truth, is 1. We get as an output of the node the value 2. From there, we can compute the loss function. And by computing the loss function, we multiply. We can also compute the derivative of the node. And we multiply them together. We get our the value for the derivative in order to update the weight. Given that the learning rate is, for example, 0.1, then the new value of the weight is becomes 0.8. And in the next epoch, if we run the same sample, we get, instead of 2, we get 1.8, which gets closer to the target value that we have set to our network. So this is an example of intuitively what happens during the forward phase, the forward phase and the backward phase. However, it's imagine that it's done in much larger scale because we have many more nodes and many more layers. So what we just described can be implemented in code like this. This is Python code. So you can see that we structure it in a way that we have one function for the forward phase and one function for the backward phase. And basically, we run each one depending on if you want to do a testing or a training phase. And you can see that we hard code the derivatives for each node. And for more complex structures, then this code would of course be more complex, and we could also have derivatives of the activation functions and so on. So one important thing to know is that when we compute the derivatives in the forward phase, then it makes sense to cache all these results so we can use them in the backward phase. So in general, every node in the network has this template, but what changes is the internal depending on what the node does. So neural networks contain multiple nodes in each layer. So it makes sense that we have multiple inputs coming to each node, and that node gives many outputs to the next levels, levels of nodes. So what happens if we have multiple outputs of a node during the backpropagation phase? So basically, what we're asking here is, how do we compute the cumulative derivative of all the outputs in a node? So that again can be solved using the chain rule. So basically, every every output of this node computes a different function, and every incoming node is a combination of these functions. So if we decompose this again, we can have partial derivatives with respect to the node, and using the chain rule, this ends up being as a summation of the partial derivatives coming in from each of the nodes. So basically, we handle all the outputs by summing their contribution to the derivative. So we said at the beginning that a lot of the nodes don't have cycles, but it turns out that nodes with cycles are important in many applications, especially considering temporal applications like speech recognition. So how do we basically do the update and the gradient accumulation when we have cycles? The idea is to basically unroll this in time. So we add extra nodes that correspond to the next time step, basically. So this loop here, what it means is that in the next time step, this node will get the previous result that was computed here. So basically what we do is we add extra nodes that capture this behavior and apply the backpropagation in the same way. So up to this point, we assume that the values that we have are scalars. But what if we have vector values? So if we have vectors, it means that we get basically, instead of one value, we get a chunk of values. So our gradients are also vectors. Basically, for each component of the vector, we have a different gradient component. And we need to find the derivative of every output with respect to every output. This basically gives us a matrix of derivatives. This is called the Jacobian matrix, and is a matrix of all the first order partial derivatives in the vector with respect to their variables. The good thing by using the Jacobian is that all our operations are now vector and matrix multiplications. So in one pass, we can multiply the Jacobian with the incoming gradient. So it makes it really easy to parallelize this process. In addition to the Jacobian, we also have the Hessian matrix, which is a square matrix of the second order partial derivatives of the vectors and their variables. And this is also used in some optimizers along with the other derivatives. So it is useful to know at least what the Hessian is if you encountered it in somewhere. So up to this point, to compute one update of the weights, we need to compute the derivative with respect to all the samples. That means that to perform one update on the weights, basically we first have to find the loss with respect to all the samples, get the gradient, and update the weights. So if you have a data set of, let's say, 1 million images, it becomes increasingly difficult and time-consuming to have this process over the whole data set. Also, if you have a large network, you need to store a lot of parameters for all the different samples. So it makes things really difficult. A way to avoid this is to use what is called a stochastic gradient descent. So the idea behind the stochastic gradient descent is to approximate the gradients using a smaller sample of our data set. Specifically, we could use all the samples, which is called batch gradient descent. We could use only one sample, which is called stochastic gradient descent, and or we can use M examples, which is called mini batch gradient descent or mini batch stochastic gradient descent. So in this case, our derivative now with respect to the loss function becomes the average over the loss computed only using a subset of these training examples. So now, remember at the beginning, we talked about an epoch that it basically is one pass through the whole training set, and an iteration being the number of updates over the weights. So using gradient descent, these two are basically one epoch result is the same as one iteration. But when we have the mini batch version, then one epoch is again a pass through the whole training set, but one iteration essentially means one weight update, which means basically processing or going through one mini batch. This is just a subtle difference that you have to keep in mind so that you don't get confused by the terminology. So in order to approximate the loss with a subset of the data, we first choose that number, which usually is much less than the total number of samples. And it's another hyperparameter that we can tune. But usually it's selected to be a power of 2, either 8, 16, and so on. And this has to do with GPU memory management. But in general, the smaller the batch size, the noisier the updates will be. That is because we are selecting them in random, so we can select 8 images that are quite different from another subset of images. So our update will move us in a direction that is not good for the whole data set. On the other hand, if we have a lot of high batch number, it will require a lot of GPU memory. So if we, for example, have 1 million images and select the batch size to be of size 64, then this will result in around 16,000 mini batches that we have to process in one epoch. This means we update the weight 16,000, but we typically select a small number for training purposes. So the version of SGD, as we saw it, can lead to some problematic situations. One of the problems is that it does not scale equally across the different dimensions. That is, if we have a high variance in one weight, then it can take longer to converge towards that direction. So in other words, we can have a fast movement in one direction and slow movement in another direction, which will make the conversion process slower. For this reason, we pick a rather small learning rate, so we avoid jumping back and forth. One solution to this is to add what is called the momentum term. So basically, the idea is that if keep on moving in one direction, we shouldn't change suddenly and start moving in another direction. This basically changes our update formula. So instead of only having the one based on the loss function, we now have this other term here that basically is a portion of the previous step that we took. So we basically have like a running average which is controlled by this parameter beta. Usually we set this to be 0.9. It was empirically found to be working well. And so basically this adds the previous step a bit so as to keep us moving in the same direction. And in practice, it has shown to make the whole process converge much faster and at the same time improve the accuracy. So there are different optimizers we can use. Traditionally, people use either the stochastic gradient descent with momentum or ADAM, which is another family of optimizers that have a different learning rate for all the parameters in the network. So we have a network we can train with backpropagation and gradient descent. Another question is, how do we decide on the number of layers or the number of neurons in each layer? So typically, as you see in the example, if we have a small number of neurons, it might not capture the whole data set. As we increase that, we end up in a case where the decision boundary is too sensitive to the data set. So it can capture probably some outliers that are in the wrong side of the data set. It could probably be either because of some mislabeling or noise. And generally, we want to avoid it. However, if we insist on training smaller networks, it can be tricky because even though they have less local minima, it makes it's more difficult to escape a bad local minima rather than in a larger network because we don't have so many parameters to change. So the idea is to basically have a larger network probably, but also ensure that through proper techniques we able to restrict its capacity to fit the whole data. And this is done through regularization. So the regularization controls how the model behaves with respect to the fitting of the data set. So the amount of outliers basically that we want to have in the model. So usually we represent regularization as another function in the loss function. In this case, it's called R, which takes as input the weight vector W for the whole network and is controlled by a regularization parameter lambda, which controls basically how strong the regularization will be. Typically, we have two regularization functions. Methods, the L1 and the L2. The L2 tries to penalize the square of the weights, whereas the L1 tries to penalize the absolute value of the weights. In effect, what this does basically is that L1 regularization enforces that some of the weights go to 0. So it only focuses practically in some of the features, while L2 has the effect of keeping the weights having small values. So basically, it tries to consider all the features that we have available. Practically, we add the regularization in our computational graph as another node that receives the weight values of the nodes that we have regularized, and is computed as part of the loss function with a gradient backpropagated to that as well. So as an example, we can see here when applying the L2 regularization, how it affects the different decision boundaries. So in all these examples, we have the same 20 neuron network. When we have a small value for the regularization penalty, you can see that the network captures really fine details in the data set. And as we increase the level of lambda, it becomes more smoother, which this has the effect of making the training error go down probably, but it looks like a much more realistic decision boundary than the further left. So regularization helps basically in controlling how complex the decision boundary of the network can be. So let's consider now a different example, an extension to what we have at this point. We consider that we have only one output, but what happens if we want to categorize an input into more than one classes? For example, for linear classifiers and SVMs, we have to train multiple classifiers when we're doing multi-class categorization. With neural networks, it's a similar setting, but all the classifiers are trained at the same time. So basically, what we do is we have as many output nodes as the classes we want to predict. And we train them together in using the same gradient descent process. But since now we have many outputs, output nodes, we have to make sure that these outputs basically sum to 1, because we're trying to find probabilities of containing of an input being in one or more in one classes. Okay, so this is more when the classes are mutually exclusive. So to do that, we first have to apply the softmax function to our output. This ensures basically that the outputs are valid probabilities and sum to 1. And then we can use the log, the categorical cross entropy with the log likelihood loss that we saw in the previous slides in order to determine our loss function. So let's see a more concrete example of using the softmax. So let's consider here that we have an animal class. Let's say that the neurons will have 3 categories, and the neurons output 3 values. So what we have to do first is apply the softmax function. This will ensure that these values are or greater than 0, and then what we get is some probabilities that sum to 1, and the highest probability is the class that we select to categorize the input. So the log loss of this network is 0.89, And we compute that by comparing with the correct probabilities, which we encode as one hot vector. So one hot vector encoding means that we have one only at the position which corresponds to the correct class. And we compare the two using the cross entropy loss. And we can then determine the loss function and update our weights accordingly. One thing that we
Hello, I can't hear anything.
Me neither.
Me neither.
You hear me? Sorry, somehow I got disconnected.
Okay.
Hello? Okay.
Here.
Okay. We're back now? Okay.
Yeah.
Okay, so I was saying that initializing the weights is an important step in towards ensuring that we have a good training and convergence at the end. So let's consider first that we initialize all the weights to 0. Hello, can you hear me?
Yeah, now we can hear you.
Yes.
Okay, so something wrong with my connection. Okay, so I was saying that let's start first and see what happens if we initialize all the weights with 0. So if we do this, what happens basically is that in every update process, all the weights will have the same value. So whenever we use the same initialization value, we get the same value for all the weights. So we don't break the symmetry of the weights, which doesn't help us into learning something. So what will happen if we have larger values? If we have larger values, it means that our activation functions like the sigmoid, which is capped at 1, and it will produce 1, which is near the slope of the gradient, and as a result, the gradient will be 0 at those points. Also, this can lead to cases where we have too high values, and the gradient also becomes too large, and we diverge from a good solution. On the other hand, if we have small weights close to 0, then the same thing will happen. We are going to have a smaller gradients, and the model will be very close to converge. This is an example of what happens with sigmoid tanh activation. So basically, we have two real numbers. We end up saturating the activation function, so our derivatives will go to 0 and we'll have no update. On the other hand, when we have small values, this means that we are close to the center of the activation function, where again we have small values for the weights, and the gradients again tend to be 0. So that was a particular problem for neural networks for some time. And a few years ago, some methods started to show up that relate the initialization strategy with the variance and the input and the fan-in input. So how many inputs does a neuron have? So if we follow that strategy and we associate the Gaussian distribution that initializes our weight with a proper variance that is corresponds to the inputs of the neuron, then this was found in practice to be a good initializer. And in combination with ReLU activations, it has shown to help networks converge faster and avoid the problems related to vanishing gradients and exploding gradients. So activation functions play a key role in training neural networks, and the choice of our activations can significantly change the performance of the training. So let's talk a bit more about some activation functions and their properties. So the sigmoid output function here is non-zero centered. So this can be a problem in cases where our inputs are positive numbers. For example, if we have pixels of an image, because both the inputs are positive, it means that our gradients will either be positive or negative for both weights at the same time. That means we are not able to change them in different ways, and this can be problematic in some cases. Tanh function, the hyperbolic tangent function, avoids that problem because it's centered at 0, so it allows to have non-negative values. But when we have too high values as input, then it will saturate and we'll have the problem of vanishing gradients or exploding gradients. So more recently, people have proposed different activation functions like the rectified linear units. These address the problem of saturation because they can have the activation can be similar. Basically, they can directly output the input value if it's above 0. This improves greatly the convergence of networks. And also, they don't saturate. However, as you will see, if we start getting negative output, kill the output and the network does not learn. So that could be a tricky point. To further address this, parametric Leaky ReLU was introduced. Basically, Leaky ReLU, as the name suggests, allows to leak non-negative values by using a parameter to propagate a small fraction of the input, and this does not completely shut off the activation. So this is a summary of the different activation functions and their range and their shape. So when building a neural network, we have to consider a lot of different parameters, like the number of layers, the initialization of the weights, how many iterations to train for, the learning rate, if we're going to use stochastic gradient descent or ADAM, what regularization to use, the batch size, and overall, all the parameters that we choose for the learning and the optimization are called in one word hyperparameters. It could basically be a very tedious process to decide which parameters to use. Some approaches rely on just doing manual search, and this is easy if you have a small problem or you have a lot of papers that describe problems, so you have a good starting point. But if you don't, then you can apply what is called a grid search. Basically, you sample your parameters, your hyperparameters under some values, and you create a grid, and then you search. And every grid point corresponds to a specific set of hyperparameters. And you basically go through each of these points and assess how good these parameters are. A similar approach is to just, instead of having this grid in a structured way, to just randomly sample a few values and train using those. So first of learning rate is also an important hyperparameter. One strategy to find it is to start with something small or large and increase it by an order of magnitude and see how the performance goes. And it helps to try different learning rates in a logarithmic fashion. This is the effect of what the different learning rates can do to the very high learning. This can spike the loss function to go really high, and we will lose. If you have too low learning rates, then the improvements will be linear. As we increase the learning rate, we'll start to see an exponential shape of the curve. And a good learning rate will result in a loss that degrades more gradually, but it will still have an exponential shape. So it's also important to start off with a small data set so that you get a good feel of the different parameters and ensure that all the code you write doesn't have any bugs or errors, so you can catch them fairly easily if you have a small and manageable data set. After that, when you start increase the number of samples, you should also introduce a training set, a validation set, and test set, just to be able to monitor the different performance metrics. So overall, the general pipeline of training neural networks involves first to initialize the weights under some strategy, then to feed forward the different samples through the network to get the actual outputs, to calculate the loss function, our error and metric, loss metric. Then we calculate the derivatives, the gradients for each layer, and we backpropagate to update the weights using a particular optimizer or rule or scheduler for the learning rate, and then we repeat this process over and over until we meet our accuracy on the validation set, or the weights do not update anymore. So now let's talk about some indicators of performance and how we can basically use them to understand what is going on with our network. So if as we said, we split the data set into 3 categories: the training, the validation, and the testing. If our training error is high, that means that we need a bigger model, or we need to train longer, or there might be something wrong with our architecture. If we start to get good training errors, it means and our validation error is high, it means that we may need more data or better regularization because the model is overfitting our training data, or we need a new model architecture. If our validation error is good, we move on to the test error, and if it is high, then we may need more training data, or we could try a different model architecture. And basically, the development and test error that you see here are a further segmentation of the data into 4 groups, but the same principles apply when we have only 3 groups. We can also monitor the loss function to see what is happening. So as the loss function starts to go down, we monitor both the validation and the training error. As we train and we see that the 2 lines start to diverge, that means that we may have started to overfit our data, so we can stop training at that point and see what we can do, or if we have already met our performance metrics. This is an example of some learning curves. So if we have the training and validation losses decreasing, that means that we are maybe underfitting. If our validation loss is lower than our training losses, that may be something our data. And to see the 2 curves to diverge, it means also that we started overfitting, and we may have to change our strategy. Whenever we see the 2 curves go together and have similar trend, it means we're doing well, but depending on if we're on a flat area or really we see a lot of jumping around of the loss, maybe our learning rate can also play a part in that. So in practice, some common mistakes that you could make is to avoid overfitting to a single batch first. So this is important, especially if you don't have a lot of experience. It's important to stay on a small data set just to make sure that all your code works fine and as it should before you move on to bigger data sets. Some other practical mistakes are to evaluate a training model without toggling its training or testing phase, which will leave some of the parameters on and could lead to really different results. Applying different pre-processing methods for validation and training could also be one of the areas of common mistakes you can make in practice. Also, make sure that the loss function you use, if it expects that the inputs are normalized probabilities or they are just logits. So now let's see a more practical example in code on how would you code a feed-forward multi-layer neural network. So the problem we want to address is that of handwritten digit recognition. We want to train a network to classify the input into the number that is present in the image. So we will basically use the MNIST dataset. It contains, if I'm not mistaken, 60,000 images for training and 10,000 images for testing. So we will take the image and we will vectorize it. Basically, we'll turn all the pixels, we will put them into one big vector, and we will pass that to through the neural network with some dense layers. We'll get the output and make it into a probability using the softmax function. We'll classify our image into the class that has the highest value. So this is code written in Keras, which is a higher level API on top of TensorFlow, which is a library developed by Google. So we start by first importing the different functions and classes we will use. There is a class for the datasets that it readily provides us with some built-in datasets. We import the layers. We are going to use the dense layer. We set up some parameters like the batch size, the number of classes, and the epochs that we want to train for. We then load the dataset using some common commands in Keras. We reshape the images into vectors, and we normalize them between 0 and 1 by dividing by the maximum pixel value. And then we turn the categories, the number of each class, into a one-hot encoded label. So we only, that is a vector that is equal to the number of classes, and we put 1 to the position that corresponds to the class of the image. Then we build the model. Basically, we have one dense layer with 512 neurons, followed by another dense layer with 512 neurons. And then we have the output layer with 10 neurons corresponding to each one of the classes. And we use the ReLU activation for all these, for all networks. And some layer that we're going to see next time called dropout that acts as a regularizer. We use the RMS prop as our optimizer to update the weights. And then we just call the fit function to start the training process. And then we just evaluate the learned model with the test set. And this particular network gets an accuracy of 98.4%, which is really high. And we can do all this in less than 50 lines of code using Keras, which is similar also with other neural network frameworks. So basically, all the complexity of doing the updates, finding the gradients, connecting the weights together, the nodes, everything is handled through the high-level APIs. So to get a better intuition on neural networks, there is a really nice app in this link. which basically allows you to play around with the number of neurons, the number of layers, and the different features. So you have two variables that you can combine to make different features. And as an output, it gives you the classification decision boundary. And I find it is really nice to play around with this and see intuitively what happens in a neural network. So I suggest you go ahead and, if you have some time, play around and get an intuition of what's going on. So neural networks. What we saw today was the standard flavor neural networks that we had in a few years ago, before the even before the deep learning came along. So in general, the neural networks are flexible and general function approximators, which they have a wide applicability across different domains. And they can be used to build extremely powerful models by adding more layers, and we'll see more in the next lecture. Of course, they have a lot of critics because theoretically they don't have a lot of good underlying foundations. They usually require huge amounts of data so they can learn reliably, and depending on their size, they also require some decent compute power to be able to learn. And they are notoriously difficult to train out of the box with a huge number of parameters that we have to set and play around with. So, ending today's class, we discussed first what is a perceptron and a neuron, and how they can be linked together to form neural networks with the goal of learning a mapping from a training set. We also talked about the different activation functions that go into neural networks and what is their impact on the training and the convergence of the learning. And we saw how we can use gradient-based optimization so that we update the weights. We talked about different loss functions and what is the impact of the loss function on the convergence of the neural network to a good solution. We saw gradient descent and stochastic gradient descent as methods for updating the weights, and how backpropagation allows us to do it in deep networks. And we also saw that they are really modular, based on modular building blocks that can be used together to build even more complex systems. And finally, we also saw that they can be universal function approximators. And next class, we will see more with regards to convolutional neural networks and how they can be more adapted to be used in images to obtain very good results, actually state-of-the-art results in the image and vision applications.